All right, let's move on with the next talk then, which is Potential Effects of Bounding Layers on Stability of Lateral Boreholes by David Martinez. Great, you're all set, David, thank you.
Okay, for some reason, I cannot see my Teams windows. I'm just looking at my presentation itself. So please give me a heads up if you stop seeing my screen or something, because as I said, the only thing I can look at right now is my own screen, okay?
Okay, David.
Okay, good morning and good afternoon. I'm David Martinez, and today I will be talking about stability challenges on horizontal boreholes and how they may be related to bedding above and below the borehole. The two issues that I'm going to be discussing are cave-ins and sections of excessive torque in parts of that lateral. I will be giving some general characteristics of these issues, and then I'm going to propose a couple of mechanisms that I feel drive these kind of issues. Of course, the reason I'm proposing these mechanisms is because they fit the characteristics that I'm going to be listing for those two. After that, we will move on to the interesting part, which is how borehole imaging can be used to de-risk the formations or the trajectory that we're going to take to drill that well. And finally, even though these two issues are kind of the way I will present it, sometimes they show very clear symptoms of what they are. They can morph into more complicated or a little different versions of themselves, and we'll be discussing those at the end. Okay, I'm in the introduction slide right now. Is that what you guys are looking at? I want to make sure there is not okay.
Yep, that's what we see.
Okay, great. Okay, cave-ins and excessive torque and reaming are two common conditions that you might encounter in long reach laterals. When I say common, I don't mean that they happen in a lot of wells. What I mean by common is that they happen in different basins, like very similar symptoms and characteristics and in completely different basins, okay? But they are not common in the sense that they happen all the time. Both of them are two different topics. When I say cave-ins and excessive torque, I don't mean that they are happening in the same well or that one leads to the other. In fact, sometimes you could tell that they are kind of mutually exclusive. One thing that they do have in common is that often you can keep drilling because it doesn't necessarily result in a complete borehole collapse. However, a sidetrack is usually performed, but it's mostly to overcome the drilling delays. It's not because you lost the hole or you got completely stuck, but it's just to a way to overcome the delays. So far, there is not a smoking gun on why they might be happening, but I think you can find specific trends in borehole images. Sorry. Okay, let's start with cave-ins. By cave-ins, I mean massive production of large tabular rock cave-ins coming from the borehole. The size and shapes I'm talking about, they may start at coffee grain size, but for the most part, they are much bigger. We are talking about a computer mouse shape and size to potato size, more or less. These large sizes indicate that they come from behind the BHA. Otherwise, they couldn't pass through the annular of the BHA and the hole. One characteristic that they have, as I said before, you can continue drilling, but you have to deal with the discharges. So of course you'll have a lot of delays. Once this issue starts, basically it persists as you keep drilling. Unless you do something to maybe move from that formation, or from a specific interface, you'll keep producing this, and you have to deal with it. So it usually leads to sidetracking to alleviate those delays. And the environments in which they occur are usually intermediate pressure and intermediate stresses. Okay. On the other hand, we have sections on the borehole that require excessive reaming and that feature excessive torque to be able to trip through them. So one particular characteristic of this kind of issue is that even when you ream extensively on your way out of the hole to do a trip for whatever reason, once you come back in, you meet that constriction again. So it's like you didn't even back ream the first time. Once again, usually you still can continue drilling, but you have to deal with the delays of back reaming all the time. And for that reason, they go on sidetrack. One peculiarity of this issue is that the casing run is usually without incident. So you can still run the casing, and you don't even see it sometimes. You don't see these constrictions. Different from the cave-ins environments, these excessive reaming intervals occur in high pressure, high isotropic stress environments. Okay, so the first, I'm going to talk about two failure mechanisms that are likely to be happening on laterals, which are different from a vertical hole. The first one will be strain release. By strain release, just you can imagine toothpaste that you go and press really, really hard, and then you suddenly open the cap, and then you have all that release or all that paste coming out of the tube. So that would be the strain release mechanism. The difference between a vertical and a horizontal borehole is that in a vertical borehole is basically you would be pressing on that tube only with your fingers. On a horizontal borehole, now you're pressing with your entire hand. So once you finally open that lid, in a horizontal borehole, you'll have more tendency of the formation to expand. What changes from, so I believe this is the main mechanism for both of the issues that we are discussing, but what changes a little bit is the configuration of the bedding in that borehole. Okay, and I'm sorry here to disappoint a little bit the geologists, but we are talking about two very simple configuration of your geology. So it's not like a super complex stratigraphy or geology theory. It's just two simple configurations. Once again, the mechanism is strain release. What changes is that when you have, let me see if I can. What we have here on the left is a configuration in which we are drilling to the deformable layer. These are unconventionals at the end of the day. So usually we'll be drilling our horizontal in a very deformable layer. And that one is going to be overlaid by a rigid layer, a harder layer, probably a lime or something like that. Once that deformable layer is free to kind of expand into the borehole, you'll have a shear interface between the rigid layer and the deformable layer, just because the tendency of the deformable layer is to expand, while the rigid layer, because it's not drilled and because in general its main characteristic is that it doesn't want to deform, will try to stay put, so you have a shear interface. So in that case, I am proposing that this is the main mechanism that starts creating those large cave-ins behind the BHA. When instead of having that configuration of a rigid layer followed by a deformable layer, what we have is a very thick, very high clay, highly deformable, high Poisson's ratio bedding. What we have instead is that the borehole has a uniform hoop stress all around. And simply what happens is that after you drill it, you would reduce the actual gauge of that borehole. This is just a minute reduction in the gauge, very, very, very small. But if we have been drilling in that layer for a long, long time, it's just enough to trap the BHA on the trips, and that's what produces the high torque. And we need all those back trimming operations. So in summary, the difference between the horizontal as compared to the vertical is that in the horizontal, you have all this strain release that is volumetric and not coming just from the little section of the formation that is being drilled. The second mechanism is rock strength anisotropy. I feel this is secondary. To me, the first mechanism is more important. However, this one is well documented anywhere. What rock strength anisotropy means is that usually a vertical sample of the rock shows us stronger, as we see here, as compared with one that is taken at an oblique direction of bedding. Okay. Usually, if you take a horizontal sample, you almost recover the entire vertical strength, but not always. Okay, this is very noisy, and actually taking samples for this kind of test is super complicated. So most people will just try to fit a curve like this. We do see evidence of this. I don't have an example right now, but you can check on these papers. Zoac has a few papers about a specific manifestation of this mechanism, and is the creation of what they call a lobe for lobe breakouts. These are not real breakouts because they are not at 180 degrees from each other, but they kind of form these four lobes around the lateral. Okay, so now for the interesting part. I'm gonna look at two examples on how we can use images to try to mitigate or to predict when these issues can happen so that we can mitigate it. Now, on the left-hand side, we are looking at an image that has the first configuration that we talk about in terms of bedding. We have a rigid layer. This is a limestone, followed by shale. And then we see a breakout forming here. We see the two lanes, and they look like run-of-the-mill breakouts. But you'll see that they don't act as your regular breakout. On the last track, we have the orientation. So this is a 90-degree borehole, which means it's horizontal. And we see that the breakout forms close to the rigid layer. And as you go deeper, deeper, deeper into that more ductile or deformable layer, it finally disappears. Okay. On this second track of the image, you see that the breakouts form on the high side and low side of this borehole. Probably worth mentioning that these wells tend to be drilled, or they are drilled in the SH main direction. Okay, so a few observations about this image. The breakout or the apparent breakout forms in the high side, low side of the borehole. The breakout position does not correspond with dominant normal stress regime. What I mean by that is that if this well is drilled in SH mean direction, we should see the breakouts on the sides of the borehole. But they appear on the top side and low side. So that means two things. Either somehow the borehole is still feeling a higher stress, maybe from the limestone, which can be in strike slip regime instead of normal stress regime, or we do have that extra shear from this rigid formation, and that's what causes the breakout to appear on the high side and low side instead of on the sides. So how do we use this kind of information? Simply, if we are lucky and we are free to choose the target, the horizontal target, anywhere on this shale, we know that from a stability point of view, you want to come down here to where the formation appears more competent. However, these breakouts are not really a big deal, and the reason you can tell is because they were able to take an image, so probably this well was drilled successfully, and you could take the image, so it doesn't really appear that in this situation you would have big issues. But then you also have to consider one thing: the bedding here on this track is around 30 degrees. So the relative attack angle of the borehole with respect to bedding is about 30 degrees. So the one thing that this is telling me is if the trajectory of the borehole is 30 degrees to bedding, the relative trajectory, then this still is a safe bet that this kind of issue is not going to happen. But this is just the low-hanging fruit. If we have an image and we have this kind of information, we can just select our safer horizon to drill. The constriction potential is a little harder to predict. What I'm showing here on this image are some transverse fractures and longitudinal fractures. They are hard to combine, but when they show up in laterals, they are very nice because now you can calibrate the vertical geomechanical model into that lateral and see where there are stress changes along the borehole. So if you start seeing sections that are very, very high stress and isotropic stress, those would have the higher potential for constriction. And once again, you either try to avoid those sections, or if you have to get into them, you recommend your drilling group to basically try to move away from them. One big advantage that you could see of LWD tools as compared to wireline tools is that theoretically we should be able to get a couple runs from the LWD tools, the one during drilling and after drilling. And if you start comparing the calipers and the borehole size between those two runs and see a difference, now we should be able to kind of tell which are the formations that have this tendency to create constrictions. But realistically, it's hard to have this kind of data in those problematic wells, because I mean, if you already know that you're having a lot of issues, you're not gonna go and try to acquire this information. It's too high the risk and too much the expense. Okay, so those first two examples from images is the kind of the low-hanging fruit. You just, let's say you have some freedom to select your targets and you see which targets are more problematic, so you just go for the easier targets. However, when you don't have that freedom, you have to deal with the problem. And the best way that I think you can do that is using the image and a lot of those information in the images beyond the typical breakout and tensile fractures to resolve a geomechanical model onto the lateral well. You may have a vertical geomechanical model, but those are usually poor resolution because when you are drilling laterally, basically the resolution of your vertical well is 1/2 foot, and that's basically the diameter of your horizontal borehole. So using the gamma ray and all this information from the horizontal logs, you can refine the vertical model and basically find more points along the borehole. And now you are able to design your trajectory in a way that it avoids a situation of high risk for these two issues to be generated. So just a little summary of what is usually done to mitigate these issues. You improve target selection when you have the opportunity to do that from something that you see in images. A lot of the mitigation comes from just operational practices. One that is typically done is you avoid those P-trap trajectories, or you try to avoid having a trough in your trajectory towards the toe of the well, because those large cave-ins may settle and then seize the BHA. when you have those severe elastic transitions, it's wise to avoid drilling parallel, like very long parallel sections to those transitions. When we have a few borehole images, you kind of characterize the geomechanic model of that lateral, and that's actually the best way, because now you do have a map of the entire lateral, and then you can predict if you have to change trajectory. For each trajectory, you can design and analyze what's going to be your more stable trajectory. Finally, it looks like pressurization cycles have to be avoided, because they can induce some fractures or some fatigue in the rock. So what people do when these problems become chronic is that they use measured pressure drilling to avoid those pressurization and depressurization cycles. As I said at the beginning, those cave-ins and high torque sections, they might morph and look like something else. So here I'm listing some of those cases. Sometimes you trip out, and then you go back in the hole and you don't find the original hole. Okay, that might be due to just a lot of your borehole caving in, and then you are just unable to kind of sense or feel for where the original borehole was. Sometimes you are able to go and find what you think is the original hole, and after drilling for some time, you go and take a survey and you're not on the original hole. That's called an accidental sidetrack. Inability to maintain a trajectory bearing. As you can imagine, when you are drilling a horizontal borehole and you are close or you are hitting that interface of the similar elastic properties, your BHA starts to bounce of the more of the stiffer formation. So that's why I'm listing this one. And sometimes when your build section is located in that big region that has that looks the weakest because of strength and anisotropy, you actually might have a full complete collapse of that build section. Finally, these 4 lobe apparent breakouts, they might be related, or they might give you an indication that if you see this issue on the basin that you're drilling, they kind of give you a first warning. This formation can be problematic. Just go into a different formation. Okay. So the conclusion that I have here is nothing that I haven't just mentioned. The 2 mechanisms that I'm proposing for these kind of issues are shear strain release and strain anisotropy, because they fit the symptoms of the issues that we have seen. Cave-ins correlate with long borehole sections that are drilled parallel to nearby layers that have a significant contrast in elasticity across the interface. Conversely, the borehole constrictions happen in thick, highly elastic layers, and the environment is now of relatively high pressure and high isotropic in situ stress. And we can squeeze even more information from borehole images in laterals to assess the instability risk and to improve the projection of the geomechanical model from vertical onto horizontal. Okay. Thank you everybody for your time, and a big shout out to my co-authors in Borehole Image Specialists that they kindly providing the image examples that I have included in this presentation.
Thank you, David. Do we have any questions? Yes, Carsten.
Yeah, thanks for your good talk, David. I have a question. On the slide, you have shown the horizontal with the transversal and the longitudinal fractures. Do you think that both are kind of induced, or maybe one set is of natural origin?
I believe they are induced, but they are the two are kind of different. Like the longitudinal, you actually induce actively depending on the mode weight that you use. The transversals usually happen because of the stress regime. Usually what they mean is that your two horizontal stresses are quite less than your normal stress, and then they just form in some sections of the borehole. And we have seen multiple. That example is from a paper that, if I'm not mistaken, is from Barnett Shale, so it's quite old. But that's not the only situation where we see those transversal fractures, and they are a little different of the longitudinal in the sense that they are created by the longitudinal stress and not the hoop stress, and they are kind of unavoidable in the sense that they don't really depend on the mode weight.
Thank you.
Okay, any other questions?